everyone. Thanks, everyone, for attending. My name is Mourad. I work at Groupon as an iOS tech lead in the merchant experience team in Berlin. And today, I'm very happy to be speaking about augmented reality and machine learning on mobile, and more specifically on the iOS. It's very important to understand the scope of the talk. So I will be giving an introduction to the two main frameworks on iOS to achieve AR and ML. And then I will be speaking or showing the easiness of how to use both of them separately. And then finally, I will end up with showing the easiness of how to integrate both of them. So for example, we can easily achieve the following demo. That's me sitting in a hotel lobby, and I was able to identify objects around me. So for example, I was able to identify that this is a computer keyboard, and that's a machine learning part. I was also able to render a 3D model explaining what this object is, which is the AR part. So what I do here has no relation to my job. I just do it for fun in my part-time, because it's really fun. The agenda is I will be speaking about what, why, how AR, then what, why, how ML, and then how both of them on the iOS. So let's get started. AR, as most of us know, it's the integration of virtual models into reality. From Apple's perspective, it's when you use your iPhone or your iPad, and then you start to see what's behind the camera, and then also you start to see virtual models interacting with the real scene. And for ARKit, it's only available on the iOS devices. So this is why I'm speaking about the iPhone and the iPad. Why AR? It can be used in many applications and many games. I picked up one example of applications and one example of games. So the following video shows one example of applications in less than a minute.
Hey, IKEA would like everyone to know about Place, our new augmented reality app. Built on Apple's new ARKit, you can easily place true-to-scale 3D models of IKEA furniture in your place. Scan, browse, select, move, and place. So that could mean less of this. And less of this. And probably more of this. We want to make it easier for people everywhere to imagine a better place. Share this place. And this place. Try place in your place.
So it's very clear here that we can make use of AR in like furniture business, so that both end users, like the merchant, will be happy because the sales will increase, and the consumer will be happy as well because the consumer can visualize how the furniture look like before the consumer takes the decision to buy. Another interesting example in the games industry is Swift Shot. This game was presented in this year WWDC, which is the Worldwide Developer Conference by Apple. And here, that was an example of ARKit version 2, which had one good feature that we can share the same virtual models across more than one device. So here, there are 3 devices, the 2 players, and also the device where we can see now the demo from. Everything we see here is realistic, except only what's above the table. And this feature is very good because it can help in implementing AR multiplayer games, but it can also be useful if we want to do distributed machine learning across multiple devices. For example, I have my app. I want to run it on a device, and then my app starts to understand the scene. But then after some time, I want to launch the same app on another device, and I don't want this other device to start learning from scratch. So it can make use of the previous learning even via Bluetooth. So we don't need here any Wi-Fi or internet connection. How AR, which is the most important part on iOS, it's using ARKit. ARKit is a framework given by Apple. It's available on iOS 11 and above, and it's available on devices with A9 chip and above, which are mostly iPhone 6s and iPhone SE as well and above. The demos that I'm going to write today are written in Swift, but of course, iOS developers, we all know that we can write in both Swift and Objective-C. ARKit comes with range of APIs, but today I'm only interested in the computer vision part. ARKit has many advantages. it's easy to use, it's mobile efficient, and it's easy to customize. So Apple solved all these challenges and give us this for free in ARKit. There are some prerequisites that we need to know before we start digging into the code and the examples, is that in AR, we want to render 3D model, right? But where do we want to render the 3D model? So it makes sense that we need to go one step back and we need to understand the scene. Scene understanding involves 3 main steps. The first step is that I need to detect plane. Plane can be vertical. Let's say I want to stick something to the wall. Or plane can be horizontal. Let's say I want to put something above table or above the floor. After this step, I want to perform a heat testing. Heat testing is a process where I convert the 2D into 3D. Why? Because, for example, let's say this is the table that I want to render the 3D model on, and this is my device. Now I can see the table from my device, but the device screen is 2D. So when I touch on the device, I need to do some kind of processing, which is the head testing, that transforms this touch, the 2D touch, into a 3D point in the 3D world space. This is the heat testing. So at this point, I detected a plane, and I know the 3D point where I want to render my model. But there is one last remaining step, which is light estimation. Because if I don't apply this, then my model cannot look realistic. My model should look differently if I put it in a dark place or a light place. There is one more step left, and actually it's not one step left. It's the first step is that I detected a plane, I put my model, but then I want to rotate and look at the model from different perspective. And this is called the tracking. Tracking means that when I start launching the app, I need to know my initial position. And then when I start to move, I need to know where am I with respect to the initial position. So that, for example, if I place model in front of myself, now I see the model from the front side. But when I walk to the side of the model, then I expect to see the model, of course, from different perspective. So we need to know all these steps. But actually, in ARKit, we don't need to know how these steps are performed. ARKit gives us this for free. So where is this from my app? Imagine that our app is in the top level now, and our app can communicate with ARKit directly, and ARKit creates for us AV Foundation and Core Motion. Of course, AR needs both camera and motion to perform the AR processing. And this is also done for free for us. So we don't need to know what are these classes, what's being done behind. And the rendering part has no relation to ARKit. So the rendering part is part of another frameworks. For example, SpriteKit, SceneKit, and Metal. From the icons, SpriteKit is 2D, SceneKit is 3D, and Metal is for custom rendering. Today, I'm going to focus on ARKit, and I'm going to focus on SceneKit because I want to draw 3D models. What are the main classes that we are going to deal with? Because it's very important to understand them and understand the relationships. Apple gives us an AR SceneView. And from the prefix of the class, we understand where does this class come from. So the prefix here is 2 prefixes, actually, AR and Scene. So I understand that this class comes from ARKit and SceneKit. How Apple achieves this? Through inheritance and composition. So this class inherits from SceneView, which contains one or more nodes in form of tree structure. So for example, I have a model, and I want to be easily changing the parts of the model, like moving the model arms or head and so on. So I have node for each part of the model. This is the SceneKit part. The ARKit part, yes, and the node contains the geometry and the material. So the geometry is like the skeleton, and the material is like the skin or the texture. And the node is what we will see when we render our model. So it's something that's we see now, but of course it's the virtual model. It's not the realistic world. And we can run actions on the node. So for example, if I want to animate the arm of the model, I can run action on the arm node so that I can start seeing it animating. And the AR SceneView composes an AR session, and it's the main class that we're going to use for AR processing. The AR session needs configuration to run. And if we go to the Xcode, if we go to the symbol navigator, we can see that the AR configuration is the base class. It gives us 3 degrees of freedom. It gives us rotation around the X, Y, and Z axis. It's like the 3D degrees image. And also, if we look at the subclasses of this class, there is a face tracking configuration, which is useful if I want to detect faces and I want to detect like the eyes and nose and so on. But I don't want this today. I'm going to focus on the world tracking configuration. What's the difference between the world tracking configuration and the AR configuration? AR configuration is 3 degrees of freedom, but world tracking configuration is 6 degrees of freedom. So it's rotation and translation along the X, Y, and Z axis, which I'm interested in today. The AR session gives us one or more frame. And frame is the main class that contains everything that's needed to render the 3D model. So the frame contains, for example, the camera orientation. It contains also the tracking state. And the tracking state is very important because the tracking can be interrupted because of many reasons. Let's say I'm using my device, and then I started to shake my device like continuously. It means that the motion is distorted and there are some noises. So now the tracking state will be kind of not stable. Also, let's say I'm holding my device and then I put my finger on the camera or something like that happened that interrupted the camera scene now. Then it means that the tracking state is unstable, and I want to do anything to the user, like asking the user, please check your environment and so on. And I need here, for example, to restart the session. I can access the frame by pulling the frame at any time I want, or by listening to a delegate that calls me back whenever there is a new frame being created. And one thing that the frame contains also that's very important is the anchor. The anchor is the handle where I need to use to attach my virtual model to it. So now it's time for the hands-on and writing some code and showing some demo. But before this, I wanted to mention that there are 2 types of AR apps. There is AR must app and AR optional app. So AR optional app means, for example, if we have a furniture app which sells furniture but also can visualize the furniture in the scene. So it means that AR here is not a must. The app still have features that doesn't need AR. And if we want to do this, we have an API that we can use to turn on and off the feature. And it means that the app is always on the store. But if, for example, we look at the Swift Shot game, it's a game that's based on AR. It means that the game will not work if there is no ARKit. So at this step, we need to write ARKit in our configuration in the Xcode project. And then it means that this app will only appear on the store for particular devices only, for devices that are iOS 11 and above and A9 chip and above. So let's start writing some code. If you remember, the main class that we're going to deal with is the AR SceneView. And if I write this class and then I run, I don't see anything. Why? Because I didn't run the session. So if I try now to run the session, but before running the session, I need to create first the world tracking configuration. And then I can run the session, pass to it the world tracking configuration. And then now I can run. And now I start to see what's behind the camera. The voice is not very important, but just like for realistic feelings, that I was trying this a couple weeks ago. And now we can see that there is no AR processing still. Why? Because I didn't ask the world tracking configuration to detect any kind of planes, like horizontal or vertical. So in this example, I want to detect horizontal planes. And now if I run again, I still cannot see anything, right? So actually, if we go back 2 steps, when I run the session, there is AR processing being done, actually. But I don't see anything because I didn't perform any action. And now even when I decided that I want to detect horizontal planes, I don't see anything because I still didn't do any action. So here we can just enable some debugging options, like show statistics, some debugging flags, and then I can run again. And then at the bottom, there is how many frames per second. And then you start to see some small yellow points. I don't know if you see it or not. Yes? And these points are the feature points. It's like points of interests. So now I have a feeling that, OK, AR is being done now. So now I did the tracking, and I did the scene understanding, and I didn't write any code. So this is implemented by ARKit from behind. The last step that's remaining is to render my 3D model. And here I need to create a custom scene. Chameleon is a subclass of the scene. And then I need to pass it to the view. If I run again, it's still the same behavior. Why? Because of 2 reasons. The model is hidden by default, which is, it might not be the case in any other models. It's fine. But one more reason which is very important is that I didn't set the transformation of the model, right? So I want to put the model above the table, which means that the model should have the scale and the translation of the table, which is something that I didn't do. So one last part in this demo is that I need to first detect the table, right? So the table is being detected, but I need to listen to the delegate or the callback. And there is an interesting function here that's called addNode for anchor. So if I listen to this, this function will fire each time there is an anchor being detected. Anchor is not a plane. Anchor can be face, can be plane, can be feature point. So here I need to make sure that it's a plane. And then I will just show toast to make sure that I'm doing well. So if I run now, if you look at the bottom toast, it's changed. And it says that there is a plane anchor detected. One last step that I need to do is that, I keep on saying one last step, but this is the last step that I need to do is that I need to render my model. Here I make a check that if the model is already rendered, I don't need to render it again. Why? Because if I detect a plane, I don't want, when I detect a new plane, my model to jump from this plane to the other plane. So if the model is visible, I don't do anything. Otherwise, I make sure that it's a plane, and then I do two things. The first thing is that I need to set the transformation, as I explained, and then I need to show which is disabling the hidden flag in the node. And now, before I run, the part above is coming from ARKit, and also the session comes from ARKit, but the rendering part, the setting of the transformation and the show, comes from the SceneKit, but sometimes it's invisible to us because Apple merged both of them into one class. So now if I run, I'm trying to detect the plane, and then the model should show. And here you can see that it's a little bit shaky because the plane detection is not that stable. Why? There can be like several reasons. One reason is that if I scanned one part of the plane, and then I scan another part of the plane, ARKit doesn't understand that this is the same plane, right? So as long as I'm moving on the plane, there is like a plane merge being happening. And then at some point, I just need to do more scene understanding. There are many apps where when we try to launch the app, it keeps on telling you, okay, please move in the scene. Because as long as we move, as long as we understand the scene, the more stable is the table and the more stable is the virtual model. So here I try to stand up, I try to look at it from different perspective, and it looks a little bit stable. So that was for ARKit, but there is one small change just to show like the easiness of playing with the ARKit, is that let's say I want to touch on the table, and then when I touch, I want my model to jump from the previous place to the new place. But actually here, when I tried to do this, there was a crash in the QuickTime because I was recording this video using QuickTime, and there was a crash between QuickTime and somehow the logic that's being written in ARKit. Because when I touch the device, it's okay. But when I touch the device and try to move the chameleon, it constantly crashes. So I tried to implement the did pan. And for those who don't know, pan is when I touch the device and then I move my finger and then I end the touch. This is the pan gesture. So it crashes also when I leave the touch, but I could record before the crash. So it was useful, at least for now. So here I get my location on the device, and then I perform hit test because, as I mentioned, when I touch the device, I need to transform this 2D into 3D. And then here, if the hit test is not empty, before this part, I'm interested in the hit test only in the existing planes, because when I do hit testing, it can intersect with feature points, which I'm not interested in, because plane is more stable than feature points. So I'm interested in existing planes only. And here, if the hit test is not empty, it means that my finger touched a plane in the physical world. Then I get the first one. First one is the closest one to the camera. Because, for example, if I'm touching this table and there is a table behind, I'm only interested in this one. And here, what I want to do is that just change the transformation of the chameleon to the transformation of the hit. And by this, it means that the chameleon will move as long as I'm moving my finger on the screen. What I wanted to do more is that when I end the touch, if you know about chameleon feature, that it can get the color of the nearest like part of the table, for example, and I wanted it to react to this, but actually I think this part is the part that causes the QuickTime to crash. So when the state of the pan ended, there is a crash that happens. So you will not be able to see this, unfortunately, today. But if I run this, so I scan the table, and then I can see the chameleon. A little bit shaky at the beginning. Try to do more scanning before I start the pan, just to make sure that it can move on the table. And then here, this is my finger moving on the device. And as you can see, the scale is being computed, so I don't do anything. I just set the transformation. And if I move away, it's small. If I leave it, it will crash. But I could record before the crash. So that was all for ARKit part. Now it's time for ML. I will come back to the ARKit by combining both ARKit and ML. So as we all know, who is data scientist here? Okay, so most of us know that like machine learning is a subset of AI under the field of computer science, which mainly involves, or at least in my example, because it's a very big science, it mainly involves training and testing. And from Apple's perspective, ML actually is available on mostly all Apple products. So it's not the iOS-only devices, but also the TV, Apple TV, and the MacBook, and so on. So from Apple's perspective, only for today's example, on the iOS devices that you hold your device, I'm going to do some kind of image object recognition. So you hold your device, you start to see what's behind the camera, and then you start to understand the objects behind the camera. This is a separate example that I'm going to show. And then I will combine both ARKit and CoreML. Why ML? It can be used also in many applications and games, but here I started with the games first because it's more interesting. One example of games is that it can be used in RTS games, for example, and then if we want here to implement a computer player that detects or learns the strategy of the opponent to take the appropriate strategy. Another example is that it can be used in games winning, or I don't like this word, but like cheating. So it can be used to win games, right? And the following video shows this in less than a minute.
Welcome back, Stefan here. You're watching a skilled player play Super Mario World, but this player is not human. It's a computer program I wrote called Mar.io. This program started out knowing absolutely nothing about Super Mario World or Super Nintendo's. In fact, it didn't even know that pressing right on the controller would make the player go towards the end of the level. It learned all of these things through a process called neuroevolution. In this video, I want to teach you about how Mar.io learned to beat this level, Donut Plains 1, what its brain looks like, and how it's all based on actual biological evolution. So let's start out by actually looking at Mar.io's brain. Let's play it again, but this time we'll look at Mar.io's brain as it's making the decisions of what buttons to press. It's going to look a bit complicated at first, but don't worry, I'll help break it down for you.
So these awesome people, they implemented a neural network that can win all Mario levels. And one example of the applications is the iPhone photo built-in app, the people feature which can recognize faces and it can group photos based on faces. How ML, which should be the most important part, is that on iOS, we can achieve this using CoreML, so it's available on the same category of devices and OS. It's the iOS 11 and above, A9 chip and above, but also it's available on the Mac OS 10.13 and above. It's available on the Apple Watch 4 Plus, and it's available on TV OS 11 Plus. So it's almost cross-platform among Apple products. And the demos here, I'm going also to write in Swift. CoreML comes with range of APIs, but I'm only interested in the real-time image recognition. CoreML has many advantages. It runs only on device, which means that we can achieve data privacy and we can save the server costs. It also gives us this challenges solutions for free, the correctness, performance, and energy efficiency. So Apple solves this and gives us this for free in CoreML. What do we need to know before we start digging into the code is that we have a training data, and we have live data that we infer with this training data, and then it can say, okay, this object is X with Y confidence level. So for example, here it says that this object is chameleon with 98 confidence level. Whereas CoreML from my app, it's different than ARKit, so it's not directly being communicated from my app. My app can communicate with Vision, NLP, or Gameplay Kit. So this layer communicates with the CoreML, and also CoreML communicates with Accelerate and BNNS and Metal Performance shaders. The more we go down, the high customizations that we have, but of course, the more knowledge that we need to know before we move down. Here, I'm only interested in the vision part. What are the main classes? It's simpler than the ARKit, only 3 classes. So we have the image request handler, we have the CoreML request, and the CoreML model. Each class needs the next class. And once I perform here the image request handler, I get the classification results in the CoreML request. So let's go with the hands-on. So we have 3 steps, but we have also 1 step before the 3 steps. Is that first I need to drag and drop my CoreML model. And Xcode has a feature, preview feature, where we can see what's this model. So if I open this in the Xcode, I can see the name of the model. It's called MobileNet. I can see that it has type classifier. This means that this model isn't only the training data, but it's also the classifier. And I can see the author, I can see the description and the license. Once I drag and drop my model, I can start with the 3 steps that I mentioned. So first, I need to create the image request handler. But the image request handler needs both image and orientation, because, of course, taking the image in portrait is different than taking the image in landscape. But here, we can see that we need to convert it into CI image. Why? Because UI image is a data type only for iOS. And as I mentioned, CoreML is cross-platform among Apple products. So it cannot understand iOS data type. So this is why I need to convert to the CI image, which is a universal data type. And after I convert this, I can create my image request handler, pass to it the image, the orientation, and then I can ask it to perform, giving to it the CoreML request. Now comes the middle part, is the CoreML request. And if you remember, before creating the CoreML request, we need to create the last part, which is the CoreML model. And here the model takes the name of the file that I dragged and dropped. So it's the MobileNet. And then I can create now the CoreML request. And then I can listen to the handler, because in this handler, I will receive the classification result. The last part here is mapping the result into just a text saying that, OK, this is object X with Y confidence level, object A with B confidence level. So the result here that comes is an array which contains labels with confidence level, and it's sorted by the topmost confidence level. So let's say we have 4 returned results, which says like this is object X with 50% confidence level, object Y with 30% confidence level, object AB with 10%. I'm only interested in the first 2. So this code only does some validation and then picks up the 2 most, this prefix 2, and then maps them to just a string to show on the screen. So if I run this code, here I was in the same place, and I went to the reception and I asked the person working there. He was a nice person because he did what I wanted to do, what I asked for. I asked to print the chameleon that I rendered virtually on my device in a paper. And he did this for me. And he gave me the paper. And I put the paper now on the table. And I was able to classify it. So here, like CoreML says that it's 20% African chameleon. This means that now I used the output of ARKit as an input to CoreML. And if I try to take a picture from different perspective, actually it's the same, but a little bit like different lights and so on, we can see that the error is being enhanced. So it says that it's 66% African chameleon. I was just lucky here, so it's just coincidence. If I try to take another picture, it's getting enhanced 83%. So I think I'm just more lucky. One change that we can do here also to show how easy it is just to change, let's say, the classifier and the training data, is that let's say I want to enhance this classification result. So it was like, let's say on average it was 60%. I want to make it like 90 or 90 something. So here I go back to the code and I only change 1 line of code. So I change this ModelNet into Inception v3. And if I run again, I only changed the model. And if you remember, the model is the training data and the classifier. So I changed both of them, let's say. Actually, it's not. Yeah, it is both of them. No, it's not. I will explain why. So here you can say that the African chameleon is 90. It says that it's 98% African chameleon. If I try to take another picture, it says that it's 94. And I'm not trying to do workarounds, like I'm just trying to take pictures randomly. So it's clear here that Inception v3 is better. Why? By coincidence, there was a data scientist person who helped me because I didn't know why. if we look at the preview feature in the Xcode, we can see that the name is different, of course. I'm not sure if you can see the text or not. Can you see the text? Yes or no? Yes? OK. So here, like, the name is different, of course, and the classifier is the same. But I understood that the classifier from behind is not the same. So there is kind of like convolution process happening behind, and the convolution is not the same. And the size is different. And I thought that the data is different. But actually, the data is the same. So it's the same training data. And it appears that it's the same classifier, but no, it has a different convolution happening behind, which make also MobileNet has less number of parameters, which make it has less size. So MobileNet is 17 megabytes. So this makes like MobileNet faster, but with less performance. This is why Inception v3 was better. And if we compare generally what can cause this, many reasons. I mean, sometimes classifiers are good for some kind of classification, and other classifiers are better for other kind of classifications. Sometimes also maybe I'm using CoreML model that are not trained for what I want to classify. And also one reason is that, let's say I have a training data which contains snapshot of a model only from front, but live I want to classify it from the side, so it will not work. So there are many reasons here. And I didn't feel any performance issues with MobileNet. This is why, for me, Inception v3 was better. Maybe because the demo was very simple. So that was ARKit and CoreML. Now it's the time for both of them together. So we don't need to go into some prerequisites, because now we should be very good in this. And we can go directly for the hands-on. What I want to change here is that I want to get the current frame. If you remember, like in ARKit, we can pull any frame at any time. So I want to get this current frame from ARKit, and I want to pass it to the CoreML as an input image. So this means that ARKit speaks now to the CoreML. And this update CoreML function, I want to perform it, let's say, 30 times in a second, or 60 times, depends on the performance that I want to achieve. And this means that here, CoreML will continuously update a variable that's called latest prediction. So latest prediction is a variable that's always up to date with what's the object behind the camera now. So I will use this variable from CoreML, and I will perform heat test when I touch the device. And I will use both of these together to render also a 3D description of the model. And this is the first demo that we saw at the beginning of the talk. So here, ARKit speaks with CoreML, and of course speaks with SceneKit. If I run this code, this is the first demo that I showed at the beginning of the talk. And here what's happening is like CoreML trying to understand what's behind the camera. And if you look at the top, you will see the label, and it's a little bit shaky, it's not stable. Sometimes it says, yeah, now it says monitor, which is good. But if I look at the ping pong pad, it says sometimes it's a waffle, which I think makes sense when I go very close to it. And now I did some kind of workaround or hacky way to wait until it's water bottle, and then I touched the screen. I just waited. But it could classify almost everything, even like watch and so on. So to recap, I explained what's AR, and how to achieve AR on iOS through ARKit, what's ML, how to achieve it on iOS through CoreML, and how to integrate both of them together. That's all. I wanted to mention two things. If anyone wants to contact me for any reason, this is my email and my LinkedIn. And for those who are watching remotely, my LinkedIn might be changed for some reasons to this one, so feel free to try both. And the references that I used are only two sources, so developer.apple.com. I didn't write any code from scratch. So only developer.apple.com, samples, and the public GitHub, only one repository. So I didn't write any code from scratch. So that's all. I hope you are enjoying the conference, and I wish you a rest end of the conference. Thank you.